I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishna College. This is the lecture 2 of Module 11. In my previous lecture of Module 11, I discussed about the deviation from ideal gas equation, Andrew's experiment on carbon dioxide gas, critical constants, continuity of vapor and liquid, and the definition of critical constants. Now, in this lecture 2 in module 1, I will discuss today the topics. These are vapor and gas and their properties, Van der Waals equation of state for real gas, and boil temperature. Now we talk about vapor and gas. Before going to the definition of vapor and gas, I will just recapitulate few definition in my previous lecture that I have discussed in my previous lecture. What is the critical temperature, critical pressure, and critical volume? Now, below the critical temperature, I have seen the gas. By applying pressure, the gas changes into vapor, and after increasing the pressure, the vapor changes into liquid. And for a particular point, that is at the critical point, the vapor and liquid, the specific density of vapor and liquid before condensation and after condensation at the critical point is the same. Now, vapor and gas concept arises for the isothermal curve which are lying below the critical point or below the temperature at critical point. So, first of all, what is vapor and what is gas? The gas and vapor. Gas and vapor. Gas and vapor. A substance is said to be a gas. A substance is said to be a gas if it cannot be liquefied by applying pressure alone. So I write here a substance is said to be a gas a substance is said to be a gas if it cannot be liquefied be liquefied by applying pressure alone. However great the pressure may be. However great the pressure may be. So a substance is said to be a gas if it cannot be liquefied by applying pressure alone, however great the pressure may be. But a substance which can be liquefied only by applying pressure is called a vapor. What is vapor? A substance which is a substance a substance which is which is now which can be which can be which can be liquefied only by liquefied only by only by only by pressure is called a vapor. Only by pressure is called a vapor. Is called vapor. Is called vapor. So gas cannot be liquefied by applying pressure. Gas cannot be liquefied. Gas cannot be liquefied by applying pressure alone. However great the pressure may be, this is gas. And substance, the definition of the substance now which can be liquefied only by pressure is called vapor. Can be liquefied only by pressure is called vapor. This is the definition of gas and pressure. The next point is that this is point 1. The next point is that a substance below the critical temperature behaves as a vapor. Now below the critical temperature, a substance below its critical temperature 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 is behaves as a vapor behaves as a vapor behaves as a vapor. So a substance below its critical temperature behaves as a vapor, while above this temperature 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 behaves as a gas behaves as a gas behaves as a behaves as a gas. This is the gas and vapor. So the question arises, what is the properties of substance near critical point? Properties of substance near the critical point. Here the question arises, the properties of substance properties of substance of properties of substance near the critical near the critical near the critical point near the critical point. What is the properties of substance near the critical point? First one, the densities of the liquid and the vapor near the critical point are almost same. The densities are same. Densities of vapor and liquid are the same. Liquid and vapor at critical point are same. At critical point are same. This is the first point. Second point is, near the critical temperature the boundary between liquid and vapor disappears. Near the critical temperature the boundary between liquid and vapor disappears. The boundary between liquid and vapor disappears. Liquid and vapor disappears. Boundary between liquid and vapors disappears. And next point is that the compressibility of the vapor is very high near critical point, and at the critical point it is infinite. The compressibility is infinite. The compressibility of vapor is very high near the critical point, is infinite, is very high near the critical point. Near the critical point. Near the critical point. These are the properties of substance near the critical point. Now we go the next point, Van der Waals equation of real gas. Van der Waals equation of state of real gas. Now Van der Waals equation of state. Van der Waals equation. Van der Waals equation of state for real gas. Equation of state for real gas. Van der Waals equation of state for real gas. Now in deducing the equation of state for a perfect gas, we have assumed that for perfect gas we assume that for ideal gas or perfect gas, we assume that the volume of the gas molecule is 0. That means the gas molecules are point particle. And next, there are no interaction between two gas molecules and with the walls of the gaseous molecule and with the wall of the vessel of. So there is no interaction between two gas molecules and with the wall of the vessel. So here is very important 2 points. The assumption for ideal gas. I repeat again, for ideal gas we assume that the gas molecules are point particle, that means they occupy no volume. They occupy no volume. The molecules occupy no volume. Molecules occupy no volume. Molecules occupy no volume. Occupy no volume. Next, no interaction between two molecules. No interaction. No interaction between two molecules. No interaction between two molecule. Between two molecule or molecule or with the wall of the vessel of the system. These are the two main assumptions for ideal gas. But for real gas, the molecules have finite size, that means they have volume, and they exert forces on one another. For ideal gas, the molecules occupy no volume, that means they have no volume, and second is that no interaction between two molecules or with the wall of the vessels. But for real gas, molecule have volume, finite size. Molecules have finite size. Molecule have finite size, that means they occupy volume, and size, and secondly they exert forces on one another. They exert forces on one another. These are the main points of Van der Waals equation of state. Now, a molecule of real gas have finite volume. The free volume available, now I will go the deduction for Van der Waals equation. The Van der Waals equation. Since the molecules of a real gas have finite volume, the free volume available to them must be less than the actual volume of the vessel. This is interesting point. Since the molecules of real gas have finite volume, the free volume available to them must be less than the actual volume V of the vessel. For ideal gas, V means the V is the volume of the vessel, but for real gas, the volume, the free volume or available volume of molecule, but for real gas, the volume of gas or free volume less than free or available volume of the molecule, free or available volume should be less than V, then should be less than V, because the since the gas molecules have volume or they occupy volume, the free volume available to them must be less than the actual volume V of the vessel. So this is first point. The next point is that this is first point. The next point is that a molecule of a real gas is attached by other molecules. Suppose this is the vessel, a molecule is here, so the attracted by other molecule here, but a molecule which are lying here, they attracted by other molecule in this direction. This is molecule A, this is molecule B. A molecule of a real gas is attached by other molecules, attracted by other molecules. When a molecule lies well inside the vessel, it is attracted equally by other molecules. Suppose I consider a molecule A. Suppose I consider molecule A, which are inside the vessel. The molecules are attracted by other molecules equally by other molecules in all direction. So the net force on it is 0. The net force on is 0. Net force on the molecule A, net force on the molecule A, net force on A equal to net force equal to 0 for A molecule, but for B molecule experience an inward force, experience an inward force, experience an inward force due to attraction by other molecules. Experience an inward force due to attraction by other molecules. Thus, for a real gas, pressure is given by, but for real molecules, pressure is given by P ideal minus Pi, where Pi is called intrinsic pressure, where Pi is the intrinsic pressure. Pi is the intrinsic pressure. Intrinsic pressure. Pi is called intrinsic pressure. Therefore, P ideal equal to P ideal equal to P plus Pi, and here due to volume of the due to the volume of molecules for real gas, the free volume should be less than the actual volume of the vessel V, and suppose this volume, this is equal to V minus B. What is B? Now B is a constant which is arises due to the volume of the gas molecules. So I repeat again, since free or available volume should be less than actual volume of the vessel for real gas, I take it as V minus B. This is the volume for real gas, and here the pressure P equal to P ideal minus Pi, where Pi is the intrinsic pressure, because here we see that a molecule which are lying just on the wall or just before the wall, they experience an inward force. That's why the pressure for real gas should be less than the ideal gas. Therefore, P ideal equal to P plus Pi. Now, here we replace by Pi. Now, replace P by P plus Pi, and V by V minus B. Then from the ideal gas equation we know the PV equal to RT, it changes to P plus Pi into V minus B equal to RT. Now we have to equal to RT. Now we have to find the value of Pi and B. Now suppose, now this is the real gas equation or Van der Waals gas equation. This is real or Van der Waals gas equation. Now evaluation of constant B. Evaluation of constant B. Evaluation of constant B. Evaluation of constant B. Let us suppose that the gas is introduced into the vessel molecule by molecule. Suppose the gas is introduced into the vessel one by one molecule. So this is the vessel. I just introduce here first molecule, one molecule. Then the available volume of the for first molecule is V, because V is the volume of the vessel. I repeat again, now when the first molecule is introduced, it finds the entire volume V as free volume available for movement. Now when again I put another molecule here, for second molecule this is first molecule, this is second molecule. For second molecule the available volume is not the same as V, because for because the available volume of second molecule decreases due to the first molecule, because first molecule have some volume. That's why the free volume of second molecule will be V minus volume of the first molecule. That is, for first molecule available volume available volume available volume available volume equal to V. For second molecule available volume available volume available volume not the same as V, it is V minus volume of first molecule, volume of volume of first molecule first molecule volume of first molecule. This is the available volume of second molecule. So for second molecule available volume is, for second molecule available volume is available volume is available volume is V minus 4 3 pi sigma q. Now where sigma be the diameter of a molecule, where sigma is the diameter of the molecule, diameter of the molecule diameter of the molecule. Here why we consider 4 by 3 pi sigma square, not 4 by 3 pi sigma by 2 square. Why not? Because for a molecule of radius sigma by 2, this is the molecular volume, but we know that in my previous lecture that a molecule occupy a volume of the volume of sphere of influence. That means sphere of influence, this here is the concept of sphere of influence, and one molecule collide with other molecule when other molecular center is lying on the sphere of influence, then the two molecules are collide. So one molecule occupy, although the one molecular volume on the volume of one molecule is 4/3 pi sigma by 2 square, sigma by square, not sigma by square, sigma by 2 whole cube. Because of the influence of sphere, we consider the available volume will be 4/3 pi sigma q instead of 4/3 pi sigma by 2 the whole cube. This is not, because the sphere of influence, the volume of sphere of influence, this is the volume of sphere of influence, sphere of influence. This is the sphere of influence. So for second molecule, the available volume is V minus 4/3 pi sigma cube. Okay, clear? Okay, this is the available volume of second molecule. That means it is becomes V minus 4/3 8 into 4/3 pi sigma by 2 whole cube, where V is the volume of a molecule. V minus 8 into small v. Small v is the volume of a molecule. Volume of a molecule. Volume of a molecule. Volume of a molecule. V minus 8v. That means here the available volume will be volume minus V minus sphere of influence volume of first molecule. Sphere of influence volume of first molecule. Here is sphere of influence volume. Sphere of influence volume. Influence. Sphere of influence. Sphere of influence volume of first molecule. Okay. Now for free volume, now the free volume available to the third molecule. For third molecule available volume becomes equal to V minus 2 times into 8v and so on. So if n number of molecules are there, then the volume for any molecules, suppose n number of molecules, this is the total molecules of the gas, total molecules. Therefore, if there are n molecules in the whole system, then the average free volume for any molecule is average free volume of any molecule. Average free volume of any molecule. Average free volume of any molecule is 1/n V for first molecule. Second molecule is V minus 8 small v plus V minus 2 times 8 small v plus dot 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 plus V minus n minus 1 times 8v second bracket close, third bracket close. That means 1/n capital V minus 8v common, 1 plus 2 plus 3 plus dot 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 plus n minus 1 or 1/n third bracket nv minus 8v into 8V into n into n minus 1 divided by 2. That means V minus n minus 1 into 4V. Now we neglect the term 1 because n is large, therefore it will becomes V minus 4Vn. This is neglect 1 since n is large, neglect 1. Since n is large, we neglect the term 1. So the volume correction term, therefore volume correction term V minus B equal to 4Vn. Therefore V minus V equal to 4 minus indicates that B equal to 4V into n. This is the volume correction term. Small v is the volume of a molecule and n is the total number of gas molecules in the system. So B is the 4 times V into n. Now the evaluation of Pi, that means here I get the Van der Waals equation V minus 4Vn equal to RT, where B equal to 4Vn. Now we evaluate Pi. Let small n be the number of molecules per unit volume of the gas. Number of molecules per unit volume. Molecules per unit volume. Number of molecules per unit volume. This is the number of molecules per unit volume. The inward force on a molecule approaching the wall of the vessel is proportional to n. I repeat again, the inward force on a molecule approaching the wall of the vessel is proportional to n. If number of molecules is large, the inward force will be large. So the force on a molecule striking the wall is proportional to n. That means force is proportional to n, or I write here proportional to, suppose, a constant into n, K1 equal to constant. Again, the number of molecules striking per unit area, this is also proportional to n. The number of molecules striking per unit area also proportional to n. That means this is also K2 into n. K2 is another constant. Therefore, force and per unit area, it indicates the pressure. That means the inward force acting on the molecular striking unit area equal to proportional to force and striking per unit area. Force per unit area means pressure. So the intrinsic pressure, so intrinsic pressure, intrinsic pressure equal to K1n into K2n. That means proportional to n square. That means intrinsic pressure proportional to n square, that or proportional to capital N by V square, or Pi proportional to 1 by V square, since n is constant, since n equal to constant. Here I get P proportional to intrinsic pressure proportional to n by V square. That means Pi proportional to 1 by V square, because n is constant. So here I write Pi equal to A by V square. This is the intrinsic pressure where A is a constant. So if I put Pi equal to A by V square, and in the previous section I get B equal to 4Vn, then the Van der Waals equation becomes then Van der Waals equation becomes P plus A by V square into V minus 4Vn equal to RT. This is Van der Waals equation of state for real gas. This is equation of Van der Waals equation for real gas. This is Van der Waals equation of state for real gas. Van der Waals equation of state. Van der Waals equation of state for real gas. State for real gas. State for real gas. Van der Waals equation of state for real gas. The boil temperature. Now what is boil temperature? Boil temperature is the temperature at which a real gas obeys the equation of state for an ideal gas. I repeat again, boil temperature is the temperature at which a real gas obeys the equation of state for an ideal gas. That means boil temperature is a temperature when real gas behaves as an ideal gas. The ideal gas equation is PV equal to RT, and we know that the real gas Van der Waals equation is P plus A by V square into V minus B equal to RT. So at particular boil temperature, this ideal gas equation and this real gas equation will be the same. That means the real gas behaves as an ideal gas for this particular temperature is known as boil temperature. Now from real gas we have P plus A by V square into V minus B equal to RT, or P equal to RT by V minus B minus A by V square. Then PV equal to RTV V minus B divided by V minus B minus A by V. This is equal to PV. So for boil temperature PV becomes, for boil temperature PV becomes RTV TBV by V minus B minus A by V. This is for from this is from real gas. PV equal to RTBV by V minus B minus A by V. Again at boil temperature TB, PV equal to RTB. This is from ideal gas. This is from ideal gas. So at particular boil temperature these two equation will be the same. That means PV equal to RTBV by V minus B minus A by V and PV equal to RTB will be the same. That's why I write RTB equal to this. RTB equal to this. Now TB equal to minus A by V and minus V minus B by RV. Therefore I write TB equal to, TB equal to A V minus B by VRB. Now the quantity B is very small. Since B is very small, then we can write V minus B almost equal to V. Therefore TB becomes A by RB. This is the expression for boil temperature.